We are in the final stretch here. So we're in the final stretch here. Today, usually the last lecture is usually about wrapping up loose ends and talking about the final exam and saying our goodbyes. Because this is a 5-week course with 3-hour lecture, we're going to start new material, and I'm just going to warn you that this. It's a challenging topic. I'm sorry, but we have to talk about this topic. Also, for those of you who celebrate Happy Diwali, it's always fun. See, I'll be on campus on Thursday if it's still part of the holiday period. Not this campus, but at work. And usually there's always this nice setup for each holiday, and they have the foods of the region and everything. So it's a really nice thing. So it's a festive period. A couple of announcements. Homework 1 grades are posted. This was a mess because of the way the Canvas works. If you don't look at your homework submission to get the score, look under grades. There's a column called Homework 1 Final. That is the final grade for Homework 1. That used the correct rubric, applied the bonus points correctly, and all that. So in the Homework 1 submission, the points that are listed there are about 10 to 15 points off, usually 10 to 15 points lower than what you actually got. So look under Homework 1 Final. I believe I hid all the other grades so that you can't see them. So that's the one that I'm going to use. It's graded out of 110 on Canvas because it doesn't handle extra credit properly. So when I go to do the final grades, it's going to be graded out of 100, not out of 110. So just know that. A comment on the bonus problems. So there's a wide variety of experiences and technical abilities in this class, way wider than I actually anticipated. So you should not worry if you can't even attempt the bonus problems. Don't worry about it. You have the solutions, some suggested solutions. They're there for you to think about. You should try them. I mean, you may not get the right answer, but these are things that are good to think about to know where where the growth trajectory is, basically. If you look at these solutions, you're like, oh, okay, I get it. I couldn't figure it out when I did it myself, but I get where he's coming from. That shows that there's some growth there, and know that there's always room to grow and always room to improve. So that's for the people that are brand new to SQL or whose technical skills are a little bit on the lower side of average. If you're super, super advanced, and this class is maybe boring, the bonus points are really designed for you in mind, because to keep you motivated and to keep you learning and not be bored, essentially. We can get as challenging with this material as we can. We can get very challenging with it, but there's a window that I'm kind of staying within here. The same goes for the final, and I'll get to that at the end of the class. Homework 2 is currently being graded, or should be being graded. I'm only going to grade the bonus problems on this one. I graded all of the last homework. Homework 3 is due on Thursday, I believe. Double check that for me, please. But this homework assignment was meant to be shorter and slightly easier. Unfortunately, after I went and wrote up the solutions, I realized it's still a little bit on the challenging side, but I think it is on the shorter side. So half of it you can do now. The other half of it you'll be able to do after this lecture, which covers normalization and functional dependency theory. On the homework 3, not all the problems require a window function. So this is part of studying for the test. I'm not going to tell you what kind of query to write on the exam. You're going to have to be able to figure it out yourself. Some of you are going to overshoot and try to write recursive SQL or a window function for a simple select from group by where group by having. So I'm trying to get you used to that. There's at least one problem on there that does not require a window function at all. And it's not meant to be a trick, but it's meant to be there. If you do not use window functions for some of these problems, you're in for a really bad time. When I was writing the solutions, I thought, there's 2 ways to do this problem, a window function or regular SQL. Then I started writing the regular SQL way, and I think I ended up with like a subquery within a subquery within a subquery and a join. And there was a subquery in the from and in the join. It was ugly and it was repetitive. So you're going to have to use a window function on some of these. All right, so let's go ahead and get started. The first half of this lecture, must know, and we're going to go through it as much as I have to. The second part of the lecture about OLAP and data warehousing, this is kind of an expando. If I have a lot of time, I can go in great detail about every slide. If we don't have time, there's really only one or two concepts that I want you to understand out of OLAP. So let's go, without further ado, let's get into it. So 2 topics today, really three. Functional dependencies and normalization. So as we've talked about in this class, sometimes there's going to be times when you need to design a schema. And in the relational model, you do not want your schema to have redundancy in it. So you need to separate concerns and split out particular columns into other tables as needed. There's a theory, a mathematical theory behind this that we'll talk about. We have to talk about it in any kind of databases or SQL class. But most of it is intuitive. Usually when you do this normalization process, it's intuitive. You understand the data, you understand where the redundancies are, and you can get rid of them. Next, we'll talk about the difference between an RDBMS, which is what we've been playing with, MySQL, and which is sometimes called an OLTP system. We'll get to that in a moment. We're going to differentiate that from an OLAP system or a data warehouse. And moving forward, this is kind of where you graduate from this class. There's a future class, and I'm forgetting if it's the data visualization one or the data management one, 405, where you're going to be doing a little bit of data warehousing. So this is kind of graduating you from this to that class. Then we'll conclude the course talking about the final exam and a couple of words of advice that I have for you on that topic and as you continue in this program and into your career. So let's jump into functional dependencies. Oh, before I do that though, you need to watch the video from lecture 4. We did not get to talk about recursive SQL or the SQL explain. There's not a whole lot I can ask about SQL explain. Just know what it does and more or less how to use it. Recursive SQL, you do need to know, but I'm not going to ask you to write a query from scratch on it. I might ask you something else. So you should be familiar with it, but don't worry a whole lot about it. I'm not going to ask you to write anything from scratch on it. There is a bonus problem in the homework, though, where you can practice that. Anyway, back to today's topic. So normalization is the process of refactoring a schema, basically to reduce redundancy in a relation. So you take a relation that has some redundancy in it, you split out certain attributes into other relations. Now you have a series of sub-relations, so smaller relations, that you can join back together and presumably get back the original relation without much effort. Now, tables that do not have any redundancy in them, or where you've removed the redundancy, are called normalized tables. And if a table contains redundancy, we need to remove it. And that's called decomposing the table into multiple other tables. And the theory that we use to do this is called functional dependencies. Now, why normalize? Is it just a fun thing to do? I actually do kind of find it kind of fun. I find this whole topic kind of fun. But normalization, as I mentioned, reduces redundancy in tables and across a set of tables in a schema. It also is used to separate concerns in a database schema. But the most important part here is remember that the relational model strives for data integrity, and so that you never have data integrity issues. One thing that can happen when you have a denormalized table or some redundancy is that you get what are called insert, update, and delete anomalies. And we'll go through an example of what that means. It also reduces copies of a data, obviously, because it's the new table is not redundant. Typically, we want to query over a small number of columns. If we're using one table, we don't want to have to query over all 50 columns in a table or even subset them. So normalization is more than just separation of concerns. Back during lecture 1 and maybe, yeah.
I'm just wondering, is normalization like universally desirable when you're designing a schema?
Yes, in the relational model and in relational database systems, yes. In data warehousing, which we'll talk about this lecture as well, that's not necessarily true. There's a reason why, and that's actually an exercise for the class that we'll get to, why you may not want to denormalize a table in certain situations. But in the relational model, MySQL, you typically always normalize, or should. Some people decide, you know what, I'm not going to normalize this particular table. It's read heavy, so they don't normalize it. It's a decision, but you should normalize your tables in a relational database. So back in lecture 1 and 2, we saw these two beautiful tables, YouTube video and YouTube comment. And if we join these two together, we know that there's a lot of redundancy involved. For every comment, I'm gonna get the same video ID repeated. I'm gonna get the same channel ID repeated, and the same video title repeated, once for each comment. So are these two tables normalized? Without getting into exactly what that means yet, would you say these two tables are more or less normalized? Do they separate concerns?
Video is not normalized.
What's that?
The YouTube video is not normalized.
Why is it not normalized?
Because the concerns of likes and dislikes are in the same table.
The what? Oh, the count of likes and dislikes? Okay, that gets to a really good point, and I have a note to talk about that. In terms of redundant, how do I want to phrase this? In terms of raw redundancy, let's assume these numbers came out of thin air, the likes, dislikes, and views, and they were not computed from anything else. They were just stored just like that. These two tables are normalized, but there is redundancy in them though. The redundancy is that we can imagine in real life that views, likes, and dislikes are aggregated from some other table. There might be a table that lists all the video ID and a user ID, and that table basically says, this user liked this video. And we can recompute that column, this generated column, views, likes, and dislikes from that table. So that is a redundancy in this data, but that's not the type of redundancy that we're going to talk about today. So this is a redundancy. So is this. Redundant, but via aggregate. So this is actually a very bad table design in general. But in terms of what we're going to talk about today, it's actually okay. It's normalized. So if we natural join these two tables together, so we're going to talk about the natural join again. We get back a table called YouTube, and this table has redundancy in it, as I mentioned before. For every comment, I get back the same video ID and the same video title, repeated once for each comment. So this is going to be called a denormalized table. And these attributes here are repeated for each comment. Okay, are we good so far? Everybody just tired after 4 weeks, now 5 weeks? This is a lot of material, folks. I mean, I try not to share personal opinions about how things work, but I sometimes wonder if this should be split up or if this should be a 10-week class, especially for those that are newer to this material. It's a lot to throw at you at a time. But the previous professor did it and it worked, so here we are. Now, there's problems with the YouTube table though. There's lots of redundancy. I'm being redundant here. And there's also data integrity issues, and I'll explain what that means in a moment. There's also a delay in creating new records because of this redundancy. The normalized table, so video and comments, solves all of these issues. So let's take a look at what on earth I mean by data integrity issues. Let's say I have two relations, R1 and R2, going back to Greek letters here, and I take the natural join between them. So R1 natural join R2. I get back R. Great. But what happens now if I only use R? So R is denormalized. And let's say I want to change alpha in R to be a sigma instead. What then happens to R1 and R2? So because R is the natural join between R1 and R2, if I change alpha to sigma in R, this means I have to go back and change all the alphas in R1 to sigma and all the alphas in R2 to sigma. The database has to remember to do this. So we need to make this change in two tables. Actually three. So we make the change in R, but now we have to go back and make that same change in R1 and R2. This is costly, first of all. I have to do 3 edits here when I only need to do 1. And also, the database has to remember to go back and make those changes. Something could happen while this process is happening. We could have a power outage or something. The database can go down. And we maybe make the change in R, but we never then make the change in R1 and R2. So now I have alphas in R1 and R2 and sigmas in R. This is a data integrity problem. So we don't want to work on the denormalized table because of this. Now, there's other kinds of anomalies as well. So are there any questions on what an update anomaly is? So here, I want to change all the alphas to sigma. But in order to do that, because it's the join between the two tables, I now have to go and make the change in these subrelations as well. So are there any questions on what I mean by that?
Sorry, can you repeat it?
So if I know that R is the natural join between R1 and R2, and let's say instead of making this change, I say for me as a user, it's easier just to change the alphas in R, the denormalized table. Under the hood, the database system, because R is formed from R1 and R2, has to now go back and change all the alphas in R1 and R2 into sigmas in order to do that. If I don't do that, I have a data integrity problem. R is no longer equal to R1 bow tie R2. I have a horrible data integrity problem there. So instead what I want to do is I only want to keep R1 and R2, change alpha in R1 to sigma, and change alpha in R2 to sigma. Then if I need R, I just join the two and I get back sigma instead of alpha. I don't have to make the change in 3 places. Does that help? Cool. Now there's a couple others. I can also have an insert anomaly. Let's say I want to insert a new value for x and y here. So this table has x, y, and a. I now want to insert a new value for x, y. I think it should also say a. Let's say it's this squiggle, which I think is KSI or psi, Kasai, I don't know, and row. I want to add this thing and row into this table. So I'm going to add this and this here. Because R is the join between R1 and R2, I also have to add in the squiggle here and row here and then a squiggle here, presumably, and then whatever I had for A as well. So this means I have to wait for an update. So if I add a row into the denormalized table, I have to add the same row into R1 and R2. But I have to wait for that to happen, basically, in order to use R1 and R2, because I have to do the insert on 3 different tables now. There's another problem here as well. If I have a projection on that join, so only the denormalized table only contains a subset of the columns in R1 and R2, I'm going to have a bunch of nulls if I try to insert into R. I'm going to have nulls in R1 and nulls in R2 wherever I have an attribute that is not in the projection. So are there questions about an insert anomaly? Basically, it's the same as an update anomaly, except now if I insert a row into R, I have to insert the same row into R1 and R2. The same problem can happen. I can have a power outage before that happens, and then R1 and R2 are inconsistent. Yeah, so what do we enter for A? Is it null? We don't know. Also, we can have a delete anomaly. If we delete a value of x, say alpha, or an entire row from R, we have to now go back and delete the corresponding row from R1 and R2. Or not. It depends on what the join key is. So this just doesn't make sense. So we have these 3 anomalies, insert, update, and delete, that make it so that working with a denormalized table causes a lot of problems. Another example is, here's a better example that doesn't use Greek letters. The YouTube table. So remember, YouTube is the join between videos and comments. Let's say I decide somebody creates a new video on YouTube. We're going to add a row into YouTube for that video. But because this table is joined between the comment table and the video table, I'm going to have a bunch of attributes that are empty because there's no comment on a new video. So what do I fill in there for the comment side? We don't know. Do we just leave it null? We could do that. Or the first time somebody writes a comment on the video, we go back and find that row and then fill in the nulls with the values for that comment, the data for that comment. This is horrible to do in practice. All I want to do is when I create a new video, add a row to the video table. I don't touch the comment table. I don't touch the comment table until there's a comment on a video. So is that clear? Does that help? Okay, cool. Now, NoSQL databases and all databases that are not relational, so MongoDB, Neo4j, have no concept of normalization. This is strictly a relational concept because the join is strictly a relational concept. Strictly relational. Now, are there cases where a denormalized table is good? So in the relational model, we really try to avoid this unless we have a really good reason to use a denormalized table. In a data warehouse, is usually where we use denormalized tables, not in a database. Can you think of any cases of when it might be a good idea to use a denormalized table or when it's helpful?
In case of homework 1, when you're doing the scooter time, like when you're asking if you should compute the scooter usage time, if it's being used intensively for like second-based transactions on
Yeah.
the data warehouse, you might have to just include it in the column so you can reduce the cost of computing and maybe joining other tables.
Yeah, so you're basically right on the money, especially that last part. So his comment was that if we have something that's very intense to compute, like the duration of a scooter trip, maybe we want to keep that in a table, and then it has a little bit of redundancy. The other comment that he made was regarding joins. Many times, joins are very expensive to compute because there's so many rows in a table, and so computing these joins is very expensive. As analysts, when you work with data, you're going to have to write joins, and they're very expensive. But usually you use the result of a join over and over and over again. You don't just write a join, take the data, and then throw it away on a regular basis. Sometimes you do that. But typically, you're using the result of a join over and over. So there are cases where it is good to use a denormalized table. But this is usually only in a data warehouse, which we'll talk about today. We want to denormalize in this case if we have expensive joins that are read heavy, that are read over and over. So compute the join once, usually overnight while everybody's sleeping. Use it many times. But data may be slightly out of date. Typically as an analyst, we don't care. This is what's nice about being an analyst versus a software engineer. We can work with data that's out of date by usually a day. If you're doing an analysis, you can't keep querying the database and updating your analysis accordingly. Typically, you're supposed to be providing insights to the business. So it's okay to use old data that does not change constantly. So it's perfectly fine then to compute the join overnight and then use the result of it the following day. But again, this is typically in a data warehouse, not in a relational database system. So are there any questions on that? So this is sometimes called an exploded table in a data warehouse, but we're going to get to that. Usually I cover data warehousing before this topic in my other class, so people can usually answer that. Here I have to switch the order because we absolutely have to get through this topic. And data warehousing, I can kind of decide how in depth I want to go. Okay. So functional dependencies are how we identify redundancy within a table. This is a very theoretical concept, and much of this topic can actually be done intuitively. I think it's kind of fun to do it intuitively. But there are times when you either cannot understand what the data professional is saying because they're speaking database theory. And so narrowing everything down to mathematics and logic is a universal language, folks. If you have communication issues with anyone, Talk in terms of math and logic. Usually always works. So that's what this is for. But it's also for another thing. You may have cases where you don't understand the data, just like you don't understand a person. You don't have to understand the context of the data in order to determine if there's redundancy in it. You just have to understand the concept of a functional dependency. So I'll read what's written here, but then I'm going to summarize it and give you the cliff notes of this. We want to find all the functional dependencies in a schema. X arrow y, x to y, is true if and only if each value of x is associated with exactly one value of y. So this boils down, folks, to an x is associated with exactly one y. Some examples of a functional dependency are UID to name. Each UID maps to exactly one student. It can never map to multiple students. That is a valid functional dependency. UID to major, though, is not a functional dependency because students can have multiple majors. So one X, one student, can map to multiple Ys, majors. So X to Y does not hold there. I want to draw a couple other diagrams here. In the case that X1 maps to Y1 and Y2, we cannot say that X maps to Y. That is not a valid functional dependency. That's bad. But there is another case, though, the converse or the inverse. I can have two X's, X1 and X2, map to the same Y. That's okay. So I can have two students have the same, well, let's assume that for a moment that every student has one major. I can have two students have the same major, basically, but one student can't have multiple majors. So what does this mean? Or how else can we phrase this? I'm not going to say X functionally determines Y throughout this whole lecture. There's a variety of ways to phrase this. Sometimes we say it defines, X defines Y, or X determines Y, or X identifies Y, or uniquely identifies Y, or X maps to Y, or X implies Y. These all mean functional dependency. So is a functional dependency, it kind of looks like a function. Is it one-to-one? So this is going back, if you weren't a math major, you probably had to take real analysis and you talked about one-to-one functions. Goodness, I remember that. Is X to Y one-to-one? No. One-to-one would mean that I cannot have the case where multiple X's map to the same Y. So it is not one-to-one. On-to doesn't really, you can't really describe it here. So any questions on what a functional dependency is? This actually comes straight out of mathematics, believe it or not. If you were a math major and took abstract algebra, there's all kinds of stuff like Galois theory that is related to this. It's pretty fascinating. I've become more of a theory person since teaching. As a student, I definitely wasn't. So the take-home point here. When a functional dependency X to Y exists, it means we can split the relation in two. One containing attributes X and Y, the other containing a join key, which is X, and everything else except Y. So that's what this math is saying here. I can have X and Y in one relation, and then the other relation contains X and R minus Y. So let me see if let me draw this out for you. Let's say I have X, Y, Z, and W, and I have the functional dependency X to Y. I can decompose this table into other tables. One that is X, Y, so X to Y, and then another that contains X and everything else except Y. So X, Z, and W. And this is sometimes written as R1, XY, R2, so R can be decomposed of that. So X is a join key between the two. Does this good? Mm-hmm.
Do all y's have to have an x?
Do all y's have? Oh, so basically you're asking about on two. Do all y's have to have an x? It really depends on how you define this. If you're looking at like if y is a number, for example, you may not have an x that maps to a particular number.
Yeah.
So because the numbers are they countable or not? I'm getting in trouble here. I forget that part of abstract math. So no, I'm gonna say no for this class. Right, it may not be true. In theory, you could have an x that maps to that y, but in your data, it might not be the case.
In which case, the second table might have a column y where the x is null, but has a relation with z and w.
Yeah, yeah. Any other questions? All right. So, everything that I just said, isn't this just more or less intuitive or just based on context? Yes, it is, folks. And as analysts, most likely, you're going to use your intuition if you ever have to do this. This is more of a DBA, data engineer thing, but it's important to understand in databases. So it's a theoretical framework in case you don't understand the context of the data you're working with. You can do this hodgepodge and get and figure out whether or not you have redundancy in your data, because redundancy is bad. This topic, though, in my opinion, is more important than relational algebra. So everything that we just talked about regarding splitting these tables out based on a functional dependency comes from what's called Heath's theorem. We're not going to prove these theorems or anything, but so just bear with me here. It's basically saying that if I have R and I have the functional dependency x to y, I can decompose the tables and then rejoin them back together to get R. This left-hand table here, R1, where you project out x and y, represents x to y. And the second part here represents x to z, where z is everything. Maybe this is, I used z before, so let's just put this. X to everything but y. We don't have to be perfect in our notation here, in our theory. So x to everything else except y. Now, if you join these two tables together, you should be able to reconstruct R. This is what's called the lossless join. Lossless joins are very, very important. When we join two tables together, we don't want to gain extra rows or lose rows in the process. So what we want is we want this x, everything else, we'll put an R2. We want this. So these vertical bars, if you don't remember, is the cardinality of a set, the number of rows, the number of tuples. We want the number of tuples in this join to be equal to the number of tuples in R. If it's not, the join is lossy. So let's look at a couple of examples of lossy versus lossless. Right, we just did this. Here I have a decomposition of R. I have R1 and R2. This is for like camera manufacturers or something. Let's say I compute R1, bow tie, R2. The join key here is category. This is a natural join. So I'm going to join these two tuples together and these two tuples together. For Nikon, I'm going to join these two tuples together. And for the third tuple, which is Canon, again, I'm going to join these two tuples, 1 and 3, and these two tuples, I join tuple 1 and tuple 3. All right. So, what is the cardinality of R1, bow tie R2? How many tuples are in the result?
5.
Is it 5? 1, 2. Yeah, it's 5. What is the cardinality or the number of tuples in R? I hope you get that. 3. 3 does not equal 5. This is a lossy join. I've gained rows when I did the join. So sometimes if you write an incorrect join condition, you end up with a lossy join. This is what kept happening to me when I was early on in my career. Didn't write a good join condition, ended up getting a bunch of rows that I did not need. So this is a lossy join, even though it's gained rows. Lossy doesn't just mean that I've lost rows. So lossy. Any questions? Mm-hmm.
So how do you join R1 and R2 to get R? We need another column.
You would need a different kind of join here. You couldn't use a natural join. Yeah. Or you'd have to write a better join condition. Yeah, here, you're only given 3 attributes, but if this happened in practice, you'd have to write a better join condition or use a different one. A little bit of a toy example here. What about this one? So I have AB and I have BC. B is the join key in the natural join. If I join these two together, I join on 1 and I join on 2 here. So my result set, R1, bow tie, R2, is what? What's the size of it? How many tuples are in this join? We've been doing joins all quarter. 2. And the cardinality of R is 2. So this is lossless. I did not gain or lose any rows. Okay. Any questions on lossy versus lossless?
On the previous page,
Mm-hmm.
if you use model name as X, like the, how do you call it? The column that has functional dependency on other columns, and split it with model name included in R1 and R2. Does it think lossless shorten?
Yes. Yeah, so if you were to decompose these tables based on model name, because model name uniquely identifies these other two, you basically have X to YZ here. So you have X to Y and X to Z. If you were to decompose this table into XY and XZ, yes, that would be lossless. Yeah, so to get back to the other question regarding the join condition, if we insisted that category was the join key, we'd have to write a more sophisticated join condition. We would probably have to include the model name. So if we call this X, Y, and Z, then, let me put this in a different color. Then we would have X to Y, X to Z, and then we could decompose it R1, XY, R2, XZ. Then we would have a lossless join. But the one as written isn't. Mm-hmm.
Yeah, so if X is the primary key for that table, does it mean that all other attributes depends on X?
Yes. Yes. Yeah, well, that's the definition of primary key. Yeah. But remember, you can have candidate keys too that also uniquely identify tuples. But to answer your question, yes. Okay. We just did this example that was there. Now, on an exam or on a homework, when I ask you to find functional dependencies, there's 2 ways to do it. Just like with candidate keys and super keys. You could do it based on the context of the problem. That's the more interesting case. So I'm probably I may or may not do that. It'll have to be a really obvious context. The other option is you get 4 rows, and you're asked, based on that 4 rows, what are the functional dependencies? Usually when you only have 4 rows, there's a lot more functional dependencies than when using a context. Just because intuitively we tend to break up tables into their various use cases. So I'm gonna be very specific. I'm gonna say use the context or use the instance, just like I did with candidate keys and super keys. Now, the next couple of slides get theory. Well, this is all theory. We'll get into a little bit of math here. Don't worry, you're gonna have your notes with you for this, but there are a couple properties of these functional dependencies that you need to know. So, first is reflexivity. This is called a trivial functional dependency. If I have something like AB functionally determines A, the right-hand side is contained within the left-hand side. That's called a trivial functional dependency. If I know a student's UID and their name, I know their UID. That shouldn't be mind-blowing. That's the definition of a trivial functional dependency. That's true. Others that you might see, A to A is a tautology. A functionally determines A. And AB functionally determines A is also trivial. Now, what about augmentation? Suppose I know your UID, which means I know your name. Now, augmentation means that I can add any other attribute to UID, and it functionally determines that same right. This is so detailed, but we do need this. UID functionally determines name. That means if I add major, if now I know your major as well, I know your name from your UID, and I also know your major. That hopefully also isn't mind-blowing. Transitivity, this one should be familiar. It's a very important one. If I know your UID, if your UID uniquely identifies your dorm room number, and your dorm room number uniquely identifies your room type, transitivity says that I know your room type based on your UID. So this is transitivity. These are called Armstrong's axioms. I'm trying not to focus the rest of this concept on knowing these really, really well, because that's the undergrad class. We spend like 3 lectures doing that. Here, I don't have that time, and we really don't need to spend that much time on this. So are there any questions so far on these? Okay, these next ones are a little hairier. Let's do a proof of one of them just to show how this works. Let's say I know alpha functionally determines beta, and I know that alpha functionally determines gamma. We want to prove that alpha functionally determines both alpha, beta, and gamma. So what does this mean in practice? It means if your UID functionally determines your name. Actually, I think I have a better example here. No, I don't. And your UID functionally determines well, let's not use major here because you can have multiple. In the previous example, we'll pretend everybody has one major. And your UID functionally determines your social security number, assuming every student has one, which isn't true, but just bear with me. This means that your UID functionally determines both your name and your social security number. That's the union property. So what is the proof on how we do this? First, we're given that alpha functionally determines beta, and that alpha functionally determines gamma. We can apply augmentation to 1b, which is this one, with alpha. So we slap an alpha on both sides. This gives us alpha functionally determines alpha gamma, or just alpha functionally determines alpha gamma. 3, we can apply augmentation to 1a now. So this is alpha to beta with gamma. So now I'll have with gamma. So now I have alpha gamma functionally determines beta gamma. Now, if I look carefully at these two here, I see that I can apply transitivity. So I have alpha, if I have alpha, I can get alpha gamma here. And then from alpha gamma, I can get the beta gamma. This proves that alpha to beta gamma, the union rule. Now you saw that I went through that very, very quickly. That means that I'm not going to ask you to do a proof like this on the exam. But I want to show you that all of these properties can be derived from earlier principles. So I'll answer any questions if there are any, but we can move on here. I really just want to show you the properties here, not their proofs. So go ahead and fill that in. I'll give you some time to fill that in. And all of these can be proven this way, or not this exact proof, but similarly to this. We good to go? All right. There's a couple others, and let me get rid of this hideous color. Let's go back to red. Composition. Suppose I know your social security number. This is going to functionally determine your driver's license number. Again, we're making an assumption here that everybody has an SSN and that everybody has a driver's license number. Let's say I also know your UID. And everybody only has one major in this toy example. So I have these two functional dependencies. I have alpha to beta, and I have gamma to delta, 4 different attributes. What this is saying is that if I know your social security number and your UID together, I know your driver's license number and your major. Now, the next one, decomposition is important. This is how we decompose tables, essentially. If I have alpha functionally determines beta and gamma, then I have alpha functionally determines beta and alpha functionally determines gamma. So if UID, what was my little example here? Functionally determines your name and major, then UID functionally determines your name, and UID functionally determines your major. We have one more to get through, and then we can use these. Then we have pseudo-transitivity. This is a weird one. This says if alpha to beta and delta beta to gamma, then delta alpha to gamma. Let's say I have UID to major, and I have class level and major to advisor. So what this means is that all computer science juniors have Juliana as their advisor. All computer science sophomores have Ben as their advisor. So it depends on both the major and the class level. What this says is that UID and class level functionally determines advisor. Now, because UID functionally determines major, basically. So I get back, I'm able to rederive this one based on that. So I'll give you some time to write that down, and then we'll get into actually using this. So does this make, so I know I kind of went through this quickly. Does this more or less make sense given the little examples? So I would know these when you're doing the homework. Just refer to the slides, refer to your notes, and maybe on the exam, but I'm not going to ask you to prove things involving this. I'm trying to focus more on intuition here rather than what I do in my other class, which is a lot more theoretical than this. Believe it or not, it could get more theoretical.
In the first one, we have assumed all of us has an SSN and driving license number.
Yeah, so because of the way this is stated, we actually don't have to assume anything. It's saying, this is a statement. Social security number functionally determines driver's license number. That means I am creating a world where everybody has a social security number, and everybody has a driver's license number, and social security number uniquely identifies driver's license number. So it's not really an assumption, it's a statement. We're splitting hairs here, but it's not really an assumption. I'm stating that that is the case, basically, by writing it as a functional dependency. All right. Let's look at this little table. So this is a good exam problem because it's very simple to write. And you don't have to understand any context. You just have letters or Greek letters. So we want to find the functional dependencies that are in this table. I'm going to ask you as an exercise to go through that. Try to find all the functional dependencies that are in this table. Some of them only have one attribute on each side. There are some that have two attributes on the left, so like A, B to C. Some may have two attributes on the right. So play with that to get familiar with this concept. But here we're only checking whether or not B to C is satisfied. So let's go through this example thoroughly. Let's look at B and C. For B to C to be satisfied, this means that for every instantiation of B sub I better have exactly one value of C, not two. So let's start with B to C. I have B1, which is associated with C1 here. I'm using a curly arrow here. I don't want you to think I'm saying it's functionally determines. It's just associated with C1. I have B2 associated with C1. That's okay. I can have two X's mapped to one Y. But then I have B2 also maps to C2. That's bad. So B does not functionally determine C. So in terms of functional dependencies, that's bad. In terms of database theory, that's good. It means I don't have a redundancy. What about, so a test for you. Let's now look at C to A. And let me make sure I know the answer here. Okay. The C to A hold? No, it does not. Why? Because of C2. So C1, actually it's C1 also. C1 maps to B1. It also maps to B2, so it's automatically bad. What about now, different color, let's do this one. A to C. Does A to C hold? Does A functionally determine C? Yes, it does. A1 is associated with C1. I have another A1 associated with C1. A2 is associated with C2. I have another A2 associated with C2. And finally, I have A3 associated with C2, which is okay. So yes, A does functionally determine C. This means that in this little table, I have a redundancy. I have A to C. So what I would do is I would divide this out into AC and C and C, B, D. I don't know if that would be lossless or not, but that's one way to decompose that table. So this example is really, really important to understand. So are there any questions on how we found functional dependencies? Do you have my charger?
Yeah.
Oh, awesome.
I'm just with my
Okay, no problem. Just in case you were leaving, I wanted to make sure I get it back from you. Since we won't see each other again for a while. Thanks. Okay, great. Now, for your own studying, you should do these exercises. Actually, let's go back for a moment. What is the candidate key here? Actually, let's do this next exercise, and then we'll come back to that. I'll give you the answers for this. You should get D to B here. Are there any functional dependencies where there's one attribute on the left and two attributes on the right? No. What about the case where there are two attributes on the left and one on the right? Yes. There's A, B to C. AB to D, AB to CD, that's from the union rule, AD to B. Note that this one is derived from augmentation on A to B. It's derived from augmentation on one of these. AD to C. Actually, it's derived from here, I think. And we have another one, A to BC. No, AD to BC. So, given this answer, so go through this example on your own. What are the candidate keys for this relation? Remember, a candidate key uniquely identifies each tuple. An extension of that definition is that a candidate key means that we have a functional dependency where the candidate key functionally determines everything else in the relation. Therefore, you're going to have, when you combine both sides of the functional dependency, you get the entire set of attributes. That is literally the definition of a candidate key in terms of a functional dependency. So what are the candidate keys in this table? AB is one of them. Mm-hmm. What's the other one? AD. Yeah. So going back to the homework one, there was a very small minority of the class that really struggled with identifying candidate keys and understanding that a candidate key is a super key. So make sure you understand that because it's going to come back in this concept here. All right, let's do a more contextual example now. Here's a little table that contains winners of past US presidential elections and some data about them. We're going to make a couple of clarifying assumptions here. If I can find my note. Here it is. We're going to, actually, we'll do that on the next slide so that you can see it. One is that none of them have ever changed parties. So a person who's won president has never changed parties between elections. I don't think that's ever happened. Another assumption that we're going to make is that a president can choose a different vice president for re-election. Another one is that the VP can serve multiple presidents. So all of those constraints are actually true in US history. I'd have to go back and check, but going way back to the beginning of US history, apparently there was somebody who served as a VP twice under two different presidents. So what we're going to do here is we're going to identify all functional dependencies and how to use them to eliminate we're going to use them to eliminate redundancy. So let's use a different color here. By rule, let's look at rule 1. The candidate or the winner has never changed parties. What functional dependencies do I have there? President, yeah, so B to D. President to parties, correct. What else? There's not only a president here, there's a vice president. So C to D. That takes care of that rule. Now, rule 2 gives us some others. Rule 2 states that a president can choose a different vice president for re-election. So this sort of comes from rule 2, I guess. This one I'll just give you here because it doesn't map exactly from rule 2. We have A to B. Each election has one president, one winner for president, and one winner for vice president. We don't really vote for vice president, but you get it. There's one vice president for each election. Thus, by the union rule, we get A to BC. What are some others here? We don't have, we didn't specify constraints for these. Also assume that a VP can, okay, there's no, are there any functional dependencies for that one? Assume that a VP can serve multiple presidents. Can we infer anything from that? No, right? If a vice president can serve multiple presidents, that means I violated the definition of a functional dependency. One X is associated with two Ys. Yeah. So there's a couple others here. What are a couple of the other ones here? The big ones. There's a bunch of trivial ones as well. A is the candidate key here. So yes, I get A to B, C, D, E, F. But there's more intuitive ones here. What are a couple other ones? Any others?
A, D,
A and what?
B,
A and B, yes, that comes from the fact that A is a candidate
A
key.
and D for them.
B and what?
D for apple, D for dog.
That also comes from the fact that it's a candidate, A is a candidate key. Are there any where the left-hand side of the functional dependency is not a candidate key?
B to E
B to E. Yes, thank you.
and C to F.
B to E and C to F. Yes, thank you. We also have, right, so we did this by intuition, folks. We did not have to use any of the axioms. I did for A to B, C, just for nicety, but I don't have to. So let's make this seamless so I can write more. So what am I gonna do here to reduce redundancy? I'm going to divide out all of these functional dependencies into their own tables. I'm going to have R is equal to, I'm going to have an R1, which contains B and D. So this is president to party. I'm going to have an R2, which is vice president to party. And we'll get to this in what's wrong here in a moment. Not wrong, but weird. We're going to have B to E, which is president to their home state. We're also going to have C to F. And what else are we going to have? There's one major relationship that we haven't captured here. I've captured president to home state, vice president to home state, president to party, and vice president to party. But remember, this is a table that gives information about who won the election. Yeah.
President or vice president?
They are allowed to change. That doesn't work because, right, a president can choose a different vice president. So there's one more major one here.
A, B, C.
A, B to C. So we should also list that here as a functional dependency. It's also true that AB functionally determines C, D, E, F, and G. But we didn't have A, B, and C anywhere based on our intuition. So yes, we need A, B, C. Now, what's weird in this schema? We have two different columns here that represent the same object. So we have a vice president and a president, who are both politicians. And I have two columns, one for the home state of the president and one for the home state of the vice president. We really don't need that. Now, this redundancy isn't due to functional dependencies. It's just due to the context of the problem. So what we could do is we could treat VP and president interchangeably here. And instead what we could do is we could decompose into R1, which is candidate, party, candidate, state, and season or year candidate. So in practice, that's what you want to do. There's nothing special really about a president and a vice president. Because many vice presidents go on to become presidents. So are there any questions about this example? So, okay, we're in good time here. So you can see that the decomposition here is pretty intuitive, but it would take me a little bit of time to kind of see that At least me, I guess I'm more theoretical than I thought. But if I put letters on these columns, I can quickly identify the functional dependencies and decompose based on those. So if you don't, this is a good example because not everybody's familiar with how elections work in the United States. So if you're one of those people, you don't have to understand that except for this last part where VP and president I treated interchangeably. You don't need to know anything about elections in the United States to answer this question based on the rows that are given. You would just find the functional dependencies. That's why functional dependencies are so powerful in finding redundancy. So any other questions here? Yeah.
But what if we want to know, like, whether someone was a VP or a president? How would we find that out?
Well, then we would have to keep this schema up here. If we explicitly want to separate that out, we would have to do that. The other thing we could do is we could use the long format. We would have 2 rows for each year, one for president, one for vice president, and a bit that specifies president or vice president. Yeah, great question. That would probably be the preferable way to do it. It's less redundant. All right, so hopefully everybody has that written down. Obviously, I'm going to post this as well. That would be cruel and unusual not to. So let's go back here. Now, that's functional dependencies. We use functional dependencies to identify redundancies and decompose tables. Some decompositions, though, are better than others. Some decompositions remove more redundancy than others do. So that's the idea behind normal forms. There are different ways that we can decompose that give us different guarantees in our schema, and that also reduce more redundancy than others. There are some times when removing all redundancy may not be very useful and may make the schema somewhat ugly or not understandable, or have some other problem that we don't want. So we don't always just automatically choose the highest normal form. Sometimes we choose a lower one. Typically, we make a statement. We want a particular normal form, and we decompose to that normal form. And that's just kind of a rule. So you might work at a company where your DBA says they want all tables in 3rd normal form. So if you're asked to normalize a table, you would normalize down to 3rd normal form. We're going to talk about 4 normal forms. We're only going to talk about the 3rd normal form and Boyce-Codd normal form in depth. We're going to skip actually a lot of Boyce-Codd normal form because there's a lot of theory stuff in there that takes hours to explain. And I just want to give you the high-level concept there. 1st and 2nd normal form are very easy to discuss. There's actually 8 normal forms: 1st, 2nd, 3rd, 4th, 5th, and 6th. There's also 5th and 6th apply to time series and data warehousing, apparently. There's also some that are in between. Boyce-Codd normal form is in between 3rd and 4th. There's also a couple others. There's domain key normal form, and elementary key normal form, and essential tuple normal form. All of this content in this lecture has excellent Wikipedia articles, by the way. So if you find yourself confused, the textbook is very thorough in this. If you want, you can check the textbook. You may get frustrated pretty quickly. But Wikipedia has great articles on functional dependencies and also the normal forms. So I recommend that you look into those as well. Right, so we'll talk about 3rd normal form and BCNF mostly. Let's start with 1st normal form and just basically what is it? In 1st normal form, we basically have a decent table. Flat table, basically, flat and simple. I have no arrays. I have no lists as columns. I have no nested types, so no JSON in columns. I also have no repeated groups, which I'll explain in a minute. Also, there's a key. I don't have to have a key on every table. It's silly not to, though. And so in order to be in 1st normal form, I have to have a unique key, flat and simple types, no nesting, no repeated groups. And this one down here, no null values, is extremely controversial. Because there are often times when we do need to have nulls in a table. We just can't avoid it. Theoretically, it's not considered valid or it's not considered good practice. But we do have to have them, and we can't just say that every table under the sun is not in 1st normal form. If all of these are satisfied, the table is in at least first normal form. Now, there's a mnemonic for first, second, and third normal form. All non-key attributes, for first normal form, the mnemonic starts with all non-key attributes depend on a key. A non-key attribute means the attribute is not a key. Plus some additional constraints. So let's look at a couple of examples here. Here I have a table containing a course code, a term, and an instructor name. None of these data types are nested. They're all flat. There's no lists or arrays here or collections. There are no repeated groups. Bear with me for a moment. And there's a key. There's an implicit key. The key here is presumably going to be code and term. There's also no nulls. So because of that, this table is in first normal form at least. Let's keep going. Here's the same table, except now what I've done is I have one row per instructor, and under the course code, I have an array of courses that they teach. This is not considered a flat type. It's not a nested type either, but it's not a flat or atomic type. So because of this table is not in first normal form. Not all attributes are atomic. Now we could talk about repeated groups. I still have all atomic types here. I presumably have a key. That's actually iffy here. But the key would probably be this, but a key can't have nulls. So this is why nulls are problematic, folks. So I have nulls. Controversial, but according to the theory, it's not in first normal form. But there's a better reason why it's not in first normal form. I have 3 columns here, what are called repeated groups. They have no meaning. There's no difference between code 1 and code 2. They're classes. Who cares which course I put first? So because I have a nonsense ordering of columns, that's called a repeatable group. So nonsense order of columns. This table is not in first normal form. Now, is this where I want to put, yes. Now, let's say instead I have another table that has UID and a series of homework scores. Homework 1, 2, and 3. Would this be considered a non-repeatable group? No, because homework 1, 2, and 3 have a meaning. Homework 1 comes before homework 2, which comes before homework 3. There's a meaning here. There is no meaning to code 1, code 2, code 3. So this would be okay, assuming there's flat types, a key, which is UID, and no nulls. But this one here is not okay. Instead, what I would have is I'd have multiple rows per instructor, 1 row for each class, the long format. This is the wide format. So if I have a table and I have really low expectations and all I want to do is convert it to first normal form, all I do is remove the nulls, slap a key on it, get rid of any non-repeatable groups, and remove any attributes that are collections. That's it. Second normal form starts to get a little bit more interesting. We have to have 2 conditions. First, the table must be in first normal form. So if a table is not in first normal form, it can't be in any higher form. Now, what we're going to do is we're going to look at each attribute. The attribute is either part of a candidate key or is determined by the entire key somehow. The entire key, not by a part of the key. So this starts to get us towards separation of concerns. So the parsing of language here gets to be a little bit difficult, folks. So the attribute, if the attribute is not part of a candidate key, it must depend on the entire candidate key, not just part of it. Now, what do I mean by entire candidate key? Sometimes a candidate key can contain multiple attributes. So it follows that if a relation has no composite candidate keys, it's automatically in second normal form if it's in first normal form. So that's just a little shortcut there. Let's look at an example, but first let's talk about the mnemonic. For second normal form, the way to remember this is each attribute depends on the key, the whole key. So meaning all attributes that are in the key. So let's look at an example here. Going back to this, I'm going to give you here, because it's a little tricky, that the candidate key in this table is AB, but also AE. AE, unfortunately, I don't want AE to be a candidate key, but it is. So we have to, act accordingly. The winner of the presidential election for each, it depends on the season and the state. I have exactly one winner for that election. So what's my first functional dependency here? The main goal of this table is to show who won each state in a year. So what's my first functional dependency?
A, B to C.
Yeah, A, B to C. Are there any others? Let's focus on non-candidate keys here for the other ones.
C to D.
C to D, yep. What else? Anything with state? B to E. And this one's a little trickier. E to B. Every capital, if you know the capital, you know the state. I know the other way around is much more obvious. Great, so we have these 4 functional dependencies. In order for this table to be in second normal form, I need to look at each functional dependency, or each attribute. Each attribute here must be in the candidate key, or must be determined directly by must be determined by the entire candidate key. So A and B are good. A and B are part of the candidate key. What about C? Does C depend on the entire candidate key? It better, because we have a functional dependency A, B to C. So yes, to get the winner of the state, we have to know the year and the state. Now, what about D? D is not part of a candidate key. Can we determine D from the candidate key? Yes. What about E? E is part of one of the other candidate keys. It's part of the other candidate key. So originally when I wrote this example, and I did it wrong in front of my other class, I said this violates second normal form because of E. But E is actually, AE is actually a candidate key. So is this table in second normal form? Yes. Is this properly normalized though? Does it remove all redundancy? Is there redundant information in this table still? Yeah, so there's a lot of redundancy in this table still. I have Barack Obama listed here twice, with his birthday twice. I have California here twice, with Sacramento twice. So this is definitely not a normalized table, but it is in second normal form. So this is a more normalized table. So what would we want to do here? So one thing that we would want to do is separate out B to E and E to B. There's a reason why I'm not separating out C to D yet. That becomes too normalized. We'll get there. We do want to do that, but we won't do that right now. So a more normalized copy of this table would be A, B, C, D, and B, E. So I factored out, so I have R1 is A, B, C, D, and R2 is B, E. Yeah.
In the previous table,
Uh-huh.
E is dependent only on B, right?
E is dependent on yes,
So,
but it's a candidate key.
but isn't A B the candidate key, but it's only dependent on the part of the candidate?
AE is also a candidate key. You made the same mistake that I made. Yeah. So originally in the original example, this would have violated if AE were not a candidate key, E would violate here because E is determined from B, and B is only part of a candidate key. So I can't have any partial dependencies for second normal form. So to redo this exercise, actually get rid of actually we have to have this here. Yeah. So great question. If this were not a candidate key again, E would violate second normal form. But we're not done yet. We can still do better. We have third normal form. There's two definitions of third normal form. One's more theoretical, but it's easier to checklist. The other is based on the same wording that we've been using before. For a table to be in third normal form, it has to be in second normal form. All attributes that are not part of the candidate key must depend on the entire candidate key and only on the candidate key. It can't depend on any other attribute. So to determine a particular non-key attribute, we can only have one way to determine that attribute, and that is the candidate key. We can't get to it any other way. So a attribute that is not part of the candidate key is called a non-prime attribute. Right, so now the mnemonic becomes, we can complete the mnemonic. It only goes up to third normal form. All non-key attributes depend on a key, the whole key, and nothing but the key. So help me, COD. COD is one of the grandfathers of database theory. So, and somebody added that in, a student added that in. So it's an easy way to remember. That is third normal form, one definition of it. So let's take a look at this table again. This table, as we already know, is in second normal form. Now we want to test if it's in third normal form. So again, what are the functional dependencies that I have? We know that we have A, B to C. We also know that we have C to D. We also know, what is the candidate key now? AB. There's no AE here anymore. We got rid of it. Good riddance. So we only have AB. Now, is this table in third normal form? Let's start there. Every non-key attribute must be functionally determined by the candidate key, the whole candidate key, and nothing but the candidate key. I see two correct answers. Who says yes? Who says no? Okay, the two people who said no raised their hand. Good. It is not in third normal form. Let's look at why. A and B are okay because they're part of a candidate key. C is a non-prime attribute. It's not part of a candidate key, but it's functionally determined by a candidate key, the whole candidate key. It's not functionally determined by anything else in this table. We're going to assume here that you can have multiple candidates or multiple winners that have the same birthday. So it can't be. I cannot determine C from D, for example. What about C to D though? D is not part of the candidate key, so it's a non-prime attribute. It must be functionally determined by the candidate key, the whole candidate key, and nothing but the candidate key. So is that true here? No, because it can also be functionally determined from C only. It is related to it is determined by the candidate key, but not directly. It's determined by the candidate key by transitivity. So we'll put this in another color. We can get D by following A, B to C, and then C to D by transitivity to get A, B to D. That is a valid functional dependency, but it's valid through transitivity. So remember, every non-key attribute has to be functionally determined by the key, the whole key, and nothing but the key. Here it's determined by the candidate key and by C, which is not a part of a candidate key. So this is not in third normal form. Are there any questions? Questions about why this is not in third normal form or what we test. There's a checklist way to do this as well that might make more sense. You don't have to worry about this key, whole key, and nothing but the key. And that is presented by this man here, who used to teach the other section of my databases class as well. His name's Carlo Zaniolo. He is one of the top database theorists in the world. He used to be at UCLA, spent like 40, 50 years here, and is now retired and moved back to Italy. His last time teaching was the first quarter that we switched to remote. So I can just imagine how that went. Like, you know what, I'm done. We have 2 weeks left, I'm done. No Zoom. Can't figure out Zoom. Anyway, I don't know if that's what happened, but he was a good guy. He is the one that created a lot of this theory, especially for third normal form. He came up with a second way of defining third normal form that might be easier to understand for some of you, because it's a checklist. For every functional dependency, one of these three has to be true. Either the functional dependency is trivial, this means the right-hand side is contained in the left-hand side, gives us absolutely no information, or the left-hand side is a superkey for R, or the right-hand side is part of a candidate key. So going back to our example here, we have two functional dependencies, A, B to C, and C to D. Let's check the first one. The first one's not trivial. Is the left-hand side a superkey? Yes, it is, because it's a candidate key. So that one satisfies 3 and F. We have to now check the other one, C to D. C to D is not trivial. C is not a superkey for R. And the right-hand side, which is D, is not part of a candidate key. The candidate key is AB. All three fail. We found at least one functional dependency where all three fail. This relation is not in third normal form. So what do? We take the violating functional dependency and we split it out into its own table. We actually take each violating functional dependency and split it out into its own table. So what would we do here? C to D is a violation. So we're going to have one table that's C to D and another table that's ABC with C as the join key. So we end up with R1 ABC, R2 CD. Cool? Now if I join the two back, I get a lossless join. This is usually good enough. We now see that if we decompose the original table that contained the state and the capital, we would have we'd have three subrelations, state and capital, we'd have winter and birthday, and we'd have season, state, and winter. That would be in third normal form. That's a very strong normalization. So go Bruins here. Third normal form is usually good enough. It guarantees two theoretical properties. First, it guarantees lossless decomposition. So it means that if we decompose the table and then join them all back together, we get back the original relation without losing any rows and without gaining any new rows. There's another one here that we're not going to talk a whole lot about, and that's dependency preservation. We can still have anomalies, though, if there are overlapping candidate keys. So in the previous example where we had the state and the birthday and the winter, we had AB as a candidate key and AE as a candidate key. Those candidate keys overlap. They overlap on A. So it's possible that we can normalize even further. But what on earth is dependency preservation? I'm going to simplify the definition for this class. It just means basically x to y, a functional dependency, forms a constraint on our data. For every x, there's exactly one y associated with it. But database system, to protect data integrity, has to check that this constraint holds. We do not want to have to join two subrelations together to be able to check this constraint. If the tables are large, it's going to take forever for us just to check this stupid constraint. Dependency preservation means that each dependency is in its own subrelation and that we don't have to join tables together in order to check the constraint. So let's look at a couple of examples of that. I'll go through a couple here. Let's say I have a relation ABC with functional dependencies A to B, B to C, and A to C. And we know, because I'm giving it to you, that A is a candidate key. Convince yourself that that's the case if need be. Suppose we decompose to AB and AC. So these decompositions. Is this decomposition dependency preserving, do you think? Note that I've decomposed to AB and AC, so it's trivial that R1 preserves A to B and R2 preserves A to C. But what about B to C? This may have been lost if we cannot infer it from from our set of functional dependencies. Given A to B and A to C, is there any way to get to B to C by applying those axioms from earlier? So the answer here is no. There's no way to get B to C back just from A to B and A to C. So because of that, this decomposition is not dependency preserving. In order to check B functionally determines C, that constraint, we would have to join R1 and R2 together to check that. But database doesn't want to do that. That's very expensive. So this is another one. I could ask you a question like this, and this can actually get very, very complicated. There's very nuanced cases. I'm not interested in the nuanced cases. You should understand this type of example. If I decompose into AB, I preserved A to B. If I decomposed AC, I preserved A to C. I then have B to C left. I have no way to derive it from those two functional dependencies. I cannot preserve that dependency, B to C. What if I decompose this differently? I decompose it A to B and B to C. Now, R1 satisfies or preserves A to B, and R2 preserves B to C. But what about A to C? Is this one preserved? Right, how?
Transitivity.
By transitivity. Using A to B and B to C, I could get A to C. So A to B, B to C implies A to C by transitivity. So yes, this is a dependency preserving decomposition. And to check A to C, I don't have to join two tables together. I could just check B. I could just check A to B. Yeah. So questions about dependency preservation. Up to third normal form. So common true and false or multiple choice. Up to third normal form, we can guarantee dependency preservation and losslessness. Beyond third normal form, we lose dependency preservation, possibly, at least the guarantee. I believe up to fifth normal form, you keep losslessness. But we won't talk about fifth normal form. There's not enough interest in the world. So there's one final one I want to talk about. This is my favorite one. This is what I strive for, is Boyce-Codd normal form. It's between third and fourth normal form, so it's sometimes called 3.5 normal form. So this is Boyce and this is Codd. And here we go. Boyce-Codd normal form is very similar to third normal form, but it's more strict on the Zaniolo condition. So in third normal form under Zaniolo, each functional dependency has to either be trivial, or the left-hand side is a superkey, or the right-hand side is contained in a candidate key. We lose the third option here, folks. So BCNF is more strict. Each functional dependency must either be trivial, or the left-hand side must be a superkey. That's it. I like this one the best. It's just the easiest for me to remember. Almost every third normal form relation is also in B, C, and F, unless you have overlapping candidate keys. Then it may not be. So let's look at an example. This is one of the few examples. Well, I won't give it away. We're going to assume here that the candidate keys are AB and AC. Each student at a university is assigned an advisor based on their major. One advisor. Each student, though, can have multiple majors. Each advisor can also have multiple students, but each advisor only advises one major. So Juliana, we're going to pretend there's only one Juliana in the universe and only one Glenda in the universe. Glenda advises stats and nothing else. Juliana advises computer science and nothing else. I, though, may have two majors, CS and stats, so I have two advisors, one for each major. What are the functional dependencies here? So each student has majors, and each student, each major for that student has one advisor. So what's the first functional dependency? B to B? C to B? That is one of them, yes. Let's actually use a better color so it's easier to see. C to B, that is one of them. What is the other one? A, B to C. There are others that you can infer. You can infer AB to B, which is trivial, because B is contained in AB. There may be some others you can infer here as well. We can also infer AC to B by augmentation. This is not what I call a basis functional dependency. It's inferred by the basis functional dependencies. The basis functional dependencies come from your intuition typically. So we'll put that in a dashed box. Now, let's check something here. Is this table, I'm gonna run out of room here. Is this table in third normal form? Is it in Boyce-Codd normal form? First, is it in third normal form? So, according to the Zaniolo definition, each functional dependency has to either be trivial, the left-hand side must be a superkey, or the right-hand side must be contained in a candidate key. So A, B to C. Does that one satisfy third normal form? I see one person shaking their head. I hope to see more. A, B to C, does that satisfy third normal form? Anyone? Is AB a superkey? Yes, because AB is a candidate key. So does AB to C satisfy that condition, that first condition for third normal form? Yes. So only one of the three has to be true, folks. So now we move to the next one, C to B. Is it trivial? No. Is the left-hand side a superkey? No. Is the right-hand side contained in a candidate key? Yes. So is this table in third normal form? Yes. Great. Both satisfy third normal form, so yes. What about Boyce-Codd normal form? In Boyce-Codd normal form, each functional dependency has to either be trivial or the left-hand side is a superkey. A, B to C is not trivial. Is the left-hand side a superkey? Yes. So that one satisfies Boyce-Codd normal form, but we're not done yet. We have to check the other one. What about C to B? It's not trivial. Does this one satisfy Boyce-Codd normal form? No, because C is not a superkey. And B is right, that's it. For Boyce-Codd normal form, it's either trivial or left-hand side is a superkey. No. So this is an example. It's one of the rare examples, folks, where a table is in third normal form, but not Boyce-Codd normal form. There's only a handful of these, but I wanted to show you that. So what are the candidate keys? Well, I gave them to you, A, B, and AC. Is this relation in third normal form? Yes. Is it in Boyce-Codd normal form? No. So it's already in third normal form. We don't have to decompose it, but it's not in Boyce-Codd normal form. If I tell you that I need Boyce-Codd normal form for some reason, we have to decompose it. To decompose it, we start with the violating functional dependency and split it out into its own table. C to B violates. So I'm going to split this out into A, C, D, and B, C. Now, a little trick. Any table that only contains 2 columns and has a key is automatically B, C, and F. So that might help you on your homework. Why do I have a D in there? Right, so let's get rid of that. So it should be A, C. Let me double check this again. So we have B, C definitely, and we have A, B. And the join key is B. So, where was I going before? I don't remember what I was just saying. Then you would want to, okay, so we're done. Because R1 and R2 only contain 2 columns each, they're both in B, C, and F. The entire decomposition is in B, C, and F. B, C, and F is the highest that we'll talk about. It's the strongest. There's also fourth normal, we won't talk about this, but there's another kind of dependency called a multi-value dependency, which has to do with, it's kind of a Cartesian product between 2 sets. Something like that, I don't remember. And you can, it's really stupid to have a multi-value dependency in a data set. Typically, you only have it when you have an attribute values type table, and you can reduce the data down to fourth normal form as well. Usually once you get to B, C, and F, though, you're fine. As long as you don't have any MVDs, it's also in fourth normal form. 5th and 6th, you can read about on your own. I won't test on it. So any questions about B, C, and F? Okay, let's do one more example here, and then we'll get through the rest of these slides and take a break. Here's another way that I can ask you the problem. I try to stick with context here because this is a SQL class, and you're working with data. You're not working with letters. But these are easy questions to ask. They're easy to write. I don't have to find a data set for you. So let's say I have a relation A, B, C, D, E with functional dependencies A to B, C, C to B, D to E, and E to D. Is R and B, C, and F. So remember, B, C, and F means that each functional dependency must either be trivial or the left-hand side is a super key. We don't know what the super key is here, folks, though. So if I have A, I can derive BC. So A is not a super key because I cannot derive D or E. I basically have 2 totally separate islands here. I have A, B, and C in their own island, and I have D and E in their own islands. I have no way of getting from A, B, C to D and E. So A cannot be a super key. That automatically means this is not in B, C, and F, folks, but let's keep going with this. If I want to be sure, I have to first find out what the super key is here. What do you think the super key is? Remember, the super key uniquely identifies, functionally determines all attributes. So what would the super key be? It cannot be just A. A only determines A, B, and C. AD or AE. So the super key is AD or AE. If I have AD, I can functionally determine A, B, C, D, E. Same thing with AE. Now we check each functional dependency. For each functional dependency, it must either be trivial or the left-hand side is a super key. Let's start with A to BC. A to BC is not trivial. Is the left-hand side a super key? No, it is not AD or AE. A is not a super key. Therefore, A to BC violates, B, C, and F. Now, I would not ask you to decompose this to B, C, and F. It can be done. You would have to first take the first violating functional dependency and do a decomposition. Then you'd have to recursively do this process. Test for B, C, and F again. Find the next violating functional dependency and decompose with that. And you have to keep going for each violating functional dependency. They are not unique. There are different orderings you can choose for the violating functional dependencies. There are many different decompositions into B, C, and F. Some of them are dependency preserving, some of them are not. B, C, and F doesn't guarantee it. We're not going to go there. We're going to leave it at that. So basically, you know what a functional dependency is, how to find them. You know a little bit about first, second, third, and Boyce Codd normal form, why they're important, and how to decompose them intuitively. We didn't go through all the theory. So now this is the type of stuff that I could potentially test on is that. I won't go further than that. We won't go into full derivations of BC. I was going through my notes and I'm like, how can I kind of abbreviate this? And I'm looking through, I'm like, oh my gosh, here's like an 8-page derivation. I think it was on this problem. No, it'll be simple. It'll be something simple that's easy to decompose. Because in real life, that's all you're gonna have. If you were a DBA, it's more complicated. But as an analyst, you're not gonna have to do that. All right, bottom line, if I give you a relation, you have to infer F, or I can give you a relation R and a set of functional dependencies and ask you the highest normal form, or I can ask you, is it in 3NF or BCNF? And I could maybe ask you to decompose it into that, but that's it. So any questions on what I could ask there? Really, if it's in the notes, I can ask it. It's our last lecture. I can't get too tricky here. BCNF guarantees losslessness, folks, but it does not guarantee dependency preservation. BCNF is also not the highest normalization, so it doesn't remove all redundancy. There is still MVD redundancy. We won't talk about it. There's also some other redundancy, like computed fields, duration, and like the number of likes is actually an aggregate. There's that kind of redundancy. I believe that's dealt with in fifth normal form, but again, we're not going to talk about it. So it only removes redundancy due to functional dependencies. A functional dependency, remember, creates a constraint on the database. UID to name means that for every UID, I have exactly one name. Typically, we want our tables to be BCNF, lossless, and dependency preserving. If we can't get dependency preserving, we then use third normal form. Now, going back to SQL, and this is where I feel like a horrible person, but this is something we have to discuss. What does this have to do with SQL? Not a whole lot. You can define a primary key constraint. You can define a unique constraint. So those are forms of functional dependencies. But you cannot specify a functional dependency in a schema. You can only do it in specific use cases. So primary keys, maybe foreign keys in certain contexts, and unique keys. That's the closest we get to functional dependencies in SQL. It is a research project that some people are trying to create a database based on functional dependencies, but it's not implemented in MySQL or Postgres. But now you can see when you do a group by and an aggregate function, and you have an extra column in there, it complains. It says you cannot have this extra column. It's not in the group by, it's not in an aggregate function, and it's not functionally determined by the other columns in the select. Now you know what that means. So in MySQL, you can actually have an extra column in the select. As long as it has I don't want to say one-to-one, but as long as that is functionally determined by the other attributes in the select, then you can do it. It's not supported in the standard, but MySQL allows it. It was very bizarre that MySQL put that in their error messages because MySQL tends to be very non-theoretical. It's easier for users to use. I would expect that in Postgres, but not in MySQL. All right, so our last topic in this class, we're going to be elastic here. So I want to spend the last 30 minutes, so what is that, 3:30? Okay, so I have to go through this relatively quickly. There's only one or two things I really want to show you in OLAP and data warehousing. So let's just dig in. I'm going to go relatively quickly through the slides. If I do that, that means I don't consider it incredibly important for the exam. So, MySQL and other relational database systems are what are called OLTP systems, or online transactional processing. When you take 405, the professor there is going to talk about OLTP more. It's not a common term, but let's talk about it. OLTP is designed for frequent reads and writes. So typically this is used in a production setting, so a web app. So you're on Facebook or something, and you're clicking on things, stuff's getting written to a database. So this is happening all throughout the day. Reads and writes at random all throughout the day. But as analysts, there's another system that's a little bit more realistic for your use case. You probably will use an OLTP, a relational database system, especially at startups, and even at Google, I use a relational database system. It's based on MySQL. But at other companies, there's specific database or database-like systems that you actually use more frequently. So again, OLTP, each row is a transaction. So adding a class, sending an email, sending a Facebook message, clicking like on something. Those are all transactions. And MySQL and other relational databases and OLTP are well suited for that use case. It can also be used for analytics, of course, but there's even something better than that. So OLTP optimizes for quick reads and writes that have no pattern. All day long, reads and writes. They're based on transactions. We try to minimize redundancy, and if we need redundancy, we join tables together to solve a specific use case. They're designed for production use, so they're designed for other people to use, basically, not necessarily used for analytics, though they can be. The queries you write in OLTP are typically very complex. They involve multiple joins, stuff like that. It also abstracts data as a table, rows and columns, two-dimensional. That shouldn't be a surprise at this point. On the flip side, though, there's another kind of system that is meant to be read-only to the user. The only people that write to this type of system are other computers or data engineers. As an analyst, you will not write into this system. You will only read data from the system. And it's designed for very fast writes, very low latency, very fast reads, very low latency reads. You want to get the data quickly. You don't want to wait for a join to compute. Now, under the hood, OLTP, or a database system, is very, very different than OLAP and a data warehouse. Very different in how it stores and manipulates data. To the user, though, they actually look very similar. So to the user, there's a common programming interface called SQL to both systems, and even the way the data looks may be the same. So we'll get into that in a moment. That's OLAP. OLAP stands for Online Analytical Processing. This is a really old concept that was popular in the 90s and the early 2000s. So we don't really have OLAP-specific systems much anymore. OLAP is a concept. What we do have, though, is an implementation of OLAP called a data warehouse. Now, so OLAP is used more in concept than in implementation. And data warehouses and even database systems themselves can implement these OLAP operations. But they're completely different systems. Most of the data that you use, especially at a larger company, that's very, very heavy on analytics. So insurance companies, medical companies, student or educational companies, most of the data you use is going to come out of a data warehouse. Now, sometimes databases are used as data warehouses. So SQL Server and Oracle can be used as data warehouses. Postgres can as well, but that's not its main use. In a relational database system, data is conceptualized as rows and columns, but in OLAP, it's conceptualized as a cube. So your data doesn't only have rows and columns, it also has depth. And every attribute that you add to this schema makes the cube have more and more dimensions to it. So this is a 3D representation. It's actually a KD representation. Each attribute adds a new dimension to this cube. So a cube might look like the following. We have some sales data for Amazon. We have the location, we have the product category, and we have the shipping date. So we could draw this as a table, and to the user, this looks like a table in these systems, even though it's called a cube. So we have location, which we're gonna call the depth of the cube. We have product, which we're gonna call the height of the cube. We have the shipping date, which is the length of the cube. And we have revenue, which is called a measure. This is basically a cell within the cube. So each one of these boxes is a cell, some measure. Let's get rid of that, whoops. So there we go. So it looks to the user like a table, but it's conceptualized as a cube. It's actually a hypercube, it's k-dimensional, not 3-dimensional. But we still use cube. Now, there are two main use cases for OLAP and data warehouses. Again, they're optimized for low latency reads. So you need access to the data very quickly, and you need access to aggregated data very quickly, or pre-computed data. So there are two main use cases. One is reporting. Generated reports. Like Crystal reports or any of that software. The second is dashboarding. This is very important nowadays instead of reporting. You have some kind of user interface that represents your data. It might have a map if there's a geographical component to it. It might have a timeline slider if there's a time component to your data. And you can click these various different attributes and the entire dashboard will recompute, allowing you to drill down into more specific details about different aspects of your data. I'll show you an example of that in a moment. Now, data is transferred from a production system, which is usually a database system. This is where the users are doing all their reads and writes in a social network or whatever. That data is typically transferred into a data warehouse overnight. Why overnight? Well, it allows us to set a time period. We select all data that's before that time period, and we move it into the data warehouse or copy it into the data warehouse. This way, when you wake up the following morning, as analysts, you're not on call all the time. When you wake up the following morning, you have all the data in the data warehouse. It is a day out of date typically, but that's okay. If you want to deal with on-the-fly stuff, become a site reliability engineer that has to carry around a pager and has to debug things as they happen. Very, very stressful job. It's like being an air traffic controller. So this is a typical write schedule. So each of these little shaded boxes is a write. And this shows the difference between OLTP and OLAP. You see with OLTP, the writes occur throughout the day and at random. There's no pattern to them. But in OLAP, all the writes tend to occur overnight. Once the data is written, it's not updated throughout the day. You have to wait another day to make any updates to that data. Now, how do we get the data from the database into the data warehouse?
Just wondering, is OLTP like, you mentioned there's like a lot of uses of joins and stuff, so is it typically in like a snowflake schema kind of idea?
Yeah, so I actually used to have slides on that concept. So OLAP has 3 schemas. One's called a snowflake schema. There's a star schema, and the other one's called galaxy or constellation. So you have the same 3 schemas, both in OLTP and in OLAP as well.
Is there like a general use for like OLTP will typically default to a specific schema, or is it all use case?
OLTP can have any schema you want, which I think is usually called like constellation. It's just a mess. It just depends on the use case. OLAP for optimization reasons usually uses a star, where you have one master lookup table with a bunch of tentacles coming off of it that join to that master table of facts.
And that would be like that cube concept?
Yeah.
Okay.
Yeah.
Sure.
Yeah. So you can have, they're interchangeable. You can have star schemas in OLTP and vice versa. It's just an OLAP, or at least in the old OLAP systems, they were optimized for specific schemas. Yeah. And I actually cut those slides from the OLAP discussion. But yeah, if you're a data engineer, you would need to worry about that more. So how do we get data from the OLTP or database into OLAP or data warehousing? The reason I'm covering this is because you're going to be exposed to it. You're probably not going to do this, but you're going to be exposed to it. How this is done is using what's called an ETL job. It's a job that runs overnight. It's scheduled to run overnight. It runs a query against your database system to pull data, a select query, a join, whatever, and it writes the data into the data warehouse. So it's a Python script or something like that. And then it just writes the data into the data warehouse. It moves it from one system to another. So over here you have OLTP or RDBMS. You write data on a daily basis to OLAP or data warehouse via an ETL job. ETL stands for extract, transform, and load. The E means extract, extracting data out of a database system. The T stands for transform. A lot of stuff can happen here. Transforming could be changing data types. It could be changing what the data looks like. It could be creating aggregates. It could be a bunch of different stuff. And then L, load, just loads the data, writes the data using an insert into the data warehouse. So you're going to probably work with data engineers at some point, and you're going to hear them talk about ETL jobs. In particular, if you're missing data, you'll hear them say our ETL job crashed or something. So you'll hear that terminology frequently. And the ETL job can either pull all of the data from the beginning of time. I've seen some use cases of this. I don't understand why it's done this way on one of the teams I work with, but they actually dump their data warehouse every night and repopulate it with all of the data that's in the MySQL cloud database. So it takes a very long time to do that. Or you could incrementally update the data warehouse using new data from that previous day. You might lose some data too, depending on when the data is processed, but we're typically working with a lot of data as analysts. So as long as there's not a systematic bias in the data, we can have rows go missing at random. There's one thing about OLAP, and some data warehouses still do this, that's very different than a database system. As you're inserting the raw data into the system, it computes a bunch of group bys. It's basically a group by on steroids. If you have a bunch of attributes that are groupable attributes, it's going to compute every possible combination of group bys, every combination of attributes to group by, and give us a bunch of attributes. So for example, if I'm at UCLA and I'm looking at admissions data, and I have information about age, race, type of school the student went to, what part of a state they're from, or what state or country they're from, and I try to insert this data into an OLAP system, it's automatically going to compute all of these aggregates. It'll compute by gender, by race, by state, by location, by high school type. It'll also then compute by gender and race, by gender and school type, etc., by gender and race and school type, all of the different combinations. Basically, there's 2 to the n of them. So this number blows up really quickly. Now, the data engineer can specify that they only want to compute these aggregates on certain groups of attributes and not all of them. So that is possible to do as well. But the OLAP system does it for you. You don't have to write, necessarily, a group by statement as long as the system is already ingesting that group by for you. Then all you do is you do a query. You do a select star from some table where aggregated attribute equals gender and aggregated attribute equals a particular race, and you get back your aggregate. You don't need to write a group by or an aggregate function at all, which is really nice. So again, this is typically performed overnight. Now, there's another thing that OLAP does or data warehouses do that database systems don't do, particularly relational databases, and that is normalization. In a data warehouse, it's very, very common to have a denormalized or exploded table. What this means is that we do not care so much about normalization or having normalized tables. Typically, we only normalize down to a particular schema type. So the star schema or the constellation schema or the snowflake schema. We won't talk about those schemas, but as long as you normalize the one of those schemas, the system is actually pretty efficient and performant. We don't have to fully normalize our data though. So one thing that could happen is we could have analysts that are writing 6-way joins every day. This is all they do all day, is writing the same freaking join, and they have to run this query throughout the day. What we could do is we could hand this off to a data engineer and say, you know what? Let's actually have the data warehouse do this for us. We're going to have an exploded table. It loads in the system loads in all of the data. We then compute the join between these two tables, the 6-way join, once per night. And now the next day when you get in, you can select to your heart's content from this joined denormalized table to get quick access to data. This is very, very commonly used to populate dashboards. Denormalized tables can really be helpful. Now I have to really speed up here. We've talked about that. There are 5 main OLAP operations that have been also implemented into relational database theory. Slice, dice, roll up, drill down, and pivot. A slice is just a where. It picks out one value of one dimension. A dice is basically multiple wheres, so a where with an and or an or. A roll up, I'll show you an example of that, but it basically aggregates data from a finer grained level of a hierarchy to a more coarse grained part of the hierarchy, and I'll explain that in a moment. A drill down and a pivot. Pivot is the main one that I want to talk about because this could be done explicitly in a database system, and I was asked this in an interview. This was the table transpose thing. So we talked about this as a where. I'm just going to skim through this quickly. This is a where with an and or an or. Slice and dice, we typically only talk about slices, not dices. So don't worry too much about what a dice is specifically. We either say slice and dice or we refer to these as slices. Right? Roll up. Here's an example of a roll up. We might have data, revenue data, that's partitioned by day. So we have 3/1/22, 3/5/22, so on and so forth, and we have 1/1/1970. So we have raw data. Now it's aggregated by date. Now I can roll up to the next level in the hierarchy, which might be a week or a month. Let's say it's a month. A roll up will compute the monthly aggregates as well. So this will be for March 22, and this will be for January 1970. And it computes it for us. We don't have to do anything. We give it the raw data. It computes the daily aggregate. Then it computes the monthly aggregate, and then the yearly aggregate, and so on and so forth. So we might have quarter and year, but then we'll finally have a global aggregate out here. So this navigates up a hierarchy. So we have daily data up to global data, global aggregates, computed for you. Let's say we have this data. It has sales data that contains a year, a month, a day, an hour, and the number of sales that occurred during that hour. We want to compute at every level the number of sales that occurred. So at every level of the hierarchy. We can do that just by using a group by rollup. This is very similar to a standard aggregation, but the rollup says that I want aggregates by level of hierarchy. This is the biggest one, the highest level, and this is the lowest level. So if this is C1, C2, C3, C3 is contained within C2, contained within C1, basically. Now, I'm not going to ask you to write a roll-up on the exam, so let's keep going. This is what we would get. We would have our original daily aggregate, one for each day of each year. Then we would have our monthly aggregate. Let's say for April. We have April 2020, there were 2,662 sales. And under the day, we put null. That means this is a monthly aggregate. Then I have 2020 and null for the month and day. That means that is the aggregated sales for 2020. Finally, I have a row that only contains total sales and everything else is null. That is the global aggregated number of sales for that company. Woot. Done for us. We don't have to do it ourselves. Drill down is the opposite. So we go from the global aggregate down to daily or quarterly or whatever. I'll show you an example of this in a moment. So before we get into pivot, this is what a dashboard looks like. This is similar to one I worked on at Facebook. Basically, it shows sentiment, overall sentiment for a specific company. So in this case, it's Walmart. So Walmart is considered a slice here because I don't care about any other slice of this data. I don't care about Coca-Cola or anybody else. I'm going to get an overall sentiment score here. 40% positive, 60% negative on all their posts. Now I have gender, which is a dice. and I have location, which can be a drill down. Now, what do I do here? This gives me the overall sentiment for Walmart. If I'm only interested in female sentiment, I click on the female there, and it will repopulate the entire dashboard. Let's pretend that that's a shaded map, and that there's a pie chart there. If I click on female, the pie chart's going to change. It's now only going to aggregate by female. It dices on female. If I click on a particular state, the whole dashboard is going to repopulate, and it's only going to show me the sentiment for that particular state, which is going to change. So I talked about the Paula Deen example a while back, and for time's sake, I won't repeat it here. But what we could see is that when she made some racist comment, we could actually drill down to the West Coast, for example, or California, and you saw that the sentiment on her got very negative. But if you went into the South, it actually was a little more positive than it was before. And then when she apologized, the exact opposite happened. We wouldn't be able to see that, folks, if we didn't have these OLAP operations and a dashboard. So some of you may actually have to develop dashboards as part of your job in Tableau or maybe in Shiny for R or whatnot. Now, let's talk about the pivot operator, which is the main one that I'm interested in talking about. This is the operator that converts between long and wide mode. We talked about that there's various pros and cons to using long and wide mode. Let's say I have a table of homework scores. It originally looks like this. It looks like a spreadsheet. I have a column for each homework assignment. This is the wide format. I can also write this in terms of the long format, where I have multiple rows per student, each homework assignment on a different row. Now, there's some advantages to the long type. I can add new homework assignments easily. I can avoid nulls. I just don't put a row for that. But the wide format is, but this is also a little bit redundant. But the wide format is easier to read, but has nulls and is inflexible. And we're going to see the SQL it takes to basically convert between these two formats. Okay, we talked about that. I want to convert this from wide to long. Let's convert long to wide. So this is the more complex case. And here's a SQL. We're going to do this in 2 steps. The first thing that we're going to do is we have to create a fully specified row in the wide format. So it's going to contain UID, name, and the 4 homework assignments. So how I do this is I look at the assignment column and check what the name of the assignment is. And then I simply output the mark as homework 1 or as homework 2, whatever the name of the assignment is. That's going to get me a bunch of rows still. I'm still going to get in rows per student, but only the particular assignment that I'm looking at is going to be filled in. The rest will be zeros. Then in the second step, I aggregate by student and sum up the scores. So homework 1 is going to have 4 zeros and a score for homework 1. Homework 2 is going to have 4 zeros and a score for homework 2. Once we add all of those up, we are then going to get a fully specified row containing each homework score. So for each row, construct 5 new rows containing 5 columns, homework 1 through 5, or in this case 4. Use the case statement to place a score into the correct column and 0 elsewhere. Then collapse these 5 rows into 1 by using a sum and a group by. So here's how we would do it. First, we look at the assignment name. If it's equal to homework 1, then we plop the score into a column called homework 1. Otherwise, it's 0. We do the same thing for homework 2, 3, and 4. That's going to give me four rows per student with only 1 valid value, depending on the homework assignment I'm looking at. Then I do a final sum with a group by, and I get one fully specified row containing the homework 1, 2, 3, and 4 score. So it would look like this. There's an intermediate step here that isn't shown, but basically we'd have 4 Joe Schmoes here. One of them would have 100, 0, 0, 0, 0, 90, 0, 0, 0, 0, 58, 0, and 0000, or just no row for this assignment that he didn't submit. So the sum in the group by collapses over these columns. Any questions? Does this make sense at all? I know I went through this kind of quickly. If I had my computer, I'd show a demo. Try this out. I give you the code. I give you some sample data too that you can insert into the table, and then try this code.
Well, I use R, so then this is like a pivot long, pivot wide.
Yep.
But what if there's just so many homework, do you have to write out every single line?
So in most database systems, this isn't part of the standard. There is a function that'll let you do this wide to long, long to wide. In Postgres, it's called, I don't remember what it's called. I think crosstab or something. MySQL has its own, but it's not part of a standard. This is a standard way to do it. And if you had a million homeworks, you would not do this. You would use a function. And yeah, in R, you use spread together or pivot. The preferred way to do it now is pivot wider and pivot longer. Yeah. Now, to go the other direction, going the other direction is a little bit more redundant. I simply select each homework assignment individually, and then union that result to the results for all the other homework assignments. So what I would do here is I do a select, UID, name. I need a new column that titles the homework assignment. So I have string HW1, and then finally the score HW1. And actually, I need to be careful here with aliases. I'm going to name this assignment, and I'm going to have homework 1 score, the column, as score, or I call it mark. From homework grades, where where homework 1 is greater than 0 or is not null. And this should be an and. Then I would union all. And then I have another select, UID, name. Give this column a name, homework 2. Give this value a name. Call it assignment. Homework 2 as mark. From homework grades, where homework 2 is not null and is greater than 0. We'll just keep it at that. Union all, and then keep going like that. Very, very redundant, very ugly query. But this is an easy SQL standard way of converting from the wide format to the long format. I take the homework 1 scores, R-bind or attach the homework 2 scores. But now I have to add in another column called assignment and put the name of the assignment into that column. So are there any questions about this format? Also, this is, I gave you the code for this one as well in the SQL file. All right. So these are examples of some data warehouses: Oracle, Vertica, Hive, and SAP. There's some on the cloud. What is a data lake? I included this as a request last time I taught. There's a lot of hype. It is a concept. It is a thing. But it's a lot of marketing hype. A data lake is really just a dump of data that is not structured. It's like a file system, folks. It's like a hard disk. You just dump all of your data there, and people are trying to develop software that reads from this data lake and is able to process data from this dump of data in a relatively efficient manner. So we won't talk about that. We don't have time. But if you go through here, you can read about what a data lake is. It looks more like a swamp to me. You have a bunch of data in it that just doesn't have any format. You may never look at it again. So very quickly you run out of space in the data lake because it's just a bunch of crap that nobody's ever going to use. So this is kind of my cynical view of data lakes. HDFS, which stands for Hadoop Distributed File System for companies that use MapReduce, is probably the most commonly use data lake. It's a dump of data. You write MapReduce jobs on top of that data. All right, conclusion and exams, because I know this is on everybody's mind. It's a take-home exam. It's this Friday from 1 to 4 p.m. Everybody will start the exam at the same time. Everybody will take the exam at the same time, unless there's a couple of exceptions that I need to make. And you have 3 hours to complete it. On Brew and Learn, there should be a final exam module that shows up either today or tomorrow that contains more information about the exam. The exam itself will show up in this module once it's time to start the exam. It will not show up before that, perhaps. It just won't, there just won't be a link there. I went back and forth about how to do this if I wanted to use Respondus, which is a lockdown browser that records you on a webcam and everything. I still haven't made a final decision on how we're going to proctor this. For now, well, let's get through the rest of this. There's absolutely no collaboration allowed on this exam. That's why it's timed. It's open book, open notes, open course materials from this quarter. So anything I've provided you, anything that's in the textbooks, anything that's on the MySQL documentation website, you can use on the exam. There will be a couple of questions where I ask you to look at the documentation. This is a test. It's a test to see if you can read documentation and make sense of it and use what it says. For the time being, I'm going to require that everybody join a Zoom room. I might change this. I'll let you know. If I do this, you need to be in the room to get the code for the exam. If you're not in the room, you will not get the code to enter the exam. You will need to stay in the Zoom room for the entire period of the exam until you submit it, and we'll monitor that. And you'll have to have your camera on the whole time. I haven't decided if I'm trying to balance a couple of things here. Making sure that everybody's being honest, which it's a 5-week stressful course, so bad things can happen, and I'm aware of that. And I need a control for that. But at the same time, I also want to treat you as adults, which is very important. So I'll make a final decision about that and let you know. There's going to be 2 parts to the exam in 3 hours. The first part's conceptual. I'm going to say it's an hour to an hour and a half, a third to half of the exam. True, false, multiple choice, other kinds of objective questions like matching, whatever. There'll be some questions where you have to explain things quickly, and a couple of query questions. They're not from scratch, but you'll have to do some things with queries, and I'm not going to give you the data for that, so you have to understand the concepts there. There's going to be a second. You can use MySQL if you want. There's a trick you can use if you're really fast, is you can quickly create a test case or a data set, import it into MySQL, test the answer choices, and then pick the right run. But the idea is that it's conceptual, that you don't do that because you're going to run out of time. If you understand the concepts, you won't need to do that. The second part is writing queries from scratch. This is probably going to take the most amount of time. This one is going to take between an hour and a half to 2 hours, so most of the exam. It will not be as long as the homework. The homework, I had a different philosophy. I came up with a problem. I assigned you the problem. I then wrote the solutions and sometimes realized it was trickier than I thought it was. That's okay. That's a real life scenario. On the exam though, I can't do that. I can't have you spending 6 hours on one part of the exam. So I'm going to write simple problems that may have some tricks in them, but they're simple queries. At most, 1 subquery, folks. No more than 1 subquery. And I'll talk about that in a bit. Here, you can use MySQL. I will give you the data. You can write the query, and you can test the query in MySQL until you're convinced that it's right. There are a wide variety of levels of technical skill and SQL experience in this class. I was not prepared for that and how wide it was. So don't panic here. I have a bar that I want students to meet for an A. Some people are way above that bar and may have been extremely bored all quarter. This does not mean that the top 20% gets an A. That might be the most advanced students that are way beyond this stuff. I can't use that kind of curve here. I have a minimum bar for an A, meaning you met all of my expectations for the class and maybe even exceeded them. So an A might be a lot lower than that. I don't know what the distribution is going to be. But if you're newer to this, and maybe your technical skills aren't above average, if you've met the expectations of the class, that should be enough for an A-. So that could be a low score. I don't know what it's going to be yet. Just trust that I'm going to be fair regarding that. It's not top 20% or anything like that. It's 50% of your final grade. Tips, prioritize based on the point value. Not the ordering of the problems. The ordering tends to be however I think of the problems. When I think of them, I put them in a particular order. Prioritize by point value, your time. Write down any assumptions that you make. It doesn't guarantee credit, but it can help if we can't figure out what you're doing. If it's a valid assumption that we didn't think of, you might still get credit. Make it count. If you have doubts, write what you're thinking. Trust yourself. You've put a lot of work into this class. I know it's 5 weeks, so it's hard to build that trust, but if you've studied hard and understand most stuff, you should do okay. This exam covers everything in the course. Some cautions in writing SQL queries. I've been very picky about this because of the SQL standard and for readability. I care about readability, not efficiency. Be careful with aliasing. Simple queries are better than more complex, efficient queries. Use the correct join type. If you use left join everywhere, you're going to lose points everywhere. Use explicit join conditions. Avoid using subqueries unless absolutely necessary. That's kind of subjective. I know when you should and shouldn't use one. Case sensitivity isn't incredibly important if you're writing. You should try to be case sensitive because Postgres and other systems are case sensitive. MySQL is not. This one drives me crazy. Group by and order by, use the name of the column. Don't use a number like group by 3, 2, 1. It's valid in some database systems. It's not valid in all. You must be explicit in everything that you do. That includes using select star. You can use CTEs in other places other than recursive queries. Please only use them in recursive queries. Stick to the SQL standard like we did in lecture. We can't guarantee credit if you do something MySQL specific. I have office hours. Tuesday, tomorrow from 3 to 4. Wednesday from 3:30 to 4:30. And Thursday from 1 to 2. So I'll be available on Zoom for questions you have about the homework or about the exam or the course in general. I don't know how the final grade is going to work here. Usually the registrar doesn't open grade reporting until week 8 of the quarter. This is a 5-week course, so I may need to wait 3 weeks to post grades. I don't know how that's going to work. Maybe they'll open it early for me or I submit it to the program and they let you know what the grade is. Everything will be updated to my UCLA once that happens. So right now everything's on Brew and Learn, but it'll be propagated to my UCLA as well. Okay, what exactly is on the exam? And I'm running out of, I could do this in 7 minutes. We've already talked about the format, study everything, basically. You should know the database model, so this is lecture 1. In particular, you should know the best use, and this will be posted in the annotated notes as well. I just want your attention right now. You should know when to use which different kind of database. In particular, you should understand relational versus graph versus document. Remember, document is schemaless. You should understand keys, super keys, candidate keys, primary keys, and foreign keys, and what they mean and how to identify them. Relational algebra is going to be very similar to the homework. I'm not going to go very deep here. Hopefully you saw I was very lenient on grading the relational algebra. If it resembled relational algebra and resembled the correct algorithm, whatever, you got most of the points, if not all of them. Similar thing here. Data types, I don't know what I could ask about that, like a true and false or something. Basic SQL, very important. Select from, where, group by, having, order by, and limit. You should know the order of these keywords. Data management, not incredibly important, but you should understand insert, update, and delete. Joins, you should understand inner joins, outer joins, self joins, equa, non-equa, and you should understand the purpose of a semi and an anti-join. I understand now why semi and anti are typically not taught. It's very confusing to teach, and it's a very simple concept. So it's like, why confuse people on such a simple concept? So usually we don't teach semi and anti, but you should know what they are. You should understand various kinds of subqueries and when to use them and when not to use them. Derived tables, scalar subqueries, and correlated subqueries. Then we talked about window functions, how to use them and when to use them. They're two entirely different use cases from an aggregate function. So you should understand when to identify that. And I've made that pretty clear in the homework on how to do that. Recursive SQL and CTE, we didn't talk about thoroughly in this section. It's in a video. What I might do is have like a fill in the blank type problem on that, or ask you to write the base case or the recursive case, not the whole query itself. We had some other SQL operators like case, cast, coalesce, and the like operator that might come in useful, especially in the free response part. Finally, we talked about pivot very, very quickly. So there's like only one or, oh, I know what I could ask here. The syntax is probably not important here. I'm looking at the overall concept. Remember, there's two formats, long and wide. You should know when to use which. Query plans, I don't know what I could ask here. It might be an answer choice for a question, like how do you ensure that you have an efficient query or something? Read the documentation, A. B, check the query plan. I don't know. I don't know what I could ask there. Functional dependencies, you should be able to identify them. Normalization, you should be able to determine if a relation is in second, third, or B, C, and F, and decompose that normalization, that normal form if I ask you to do so. I could also just ask you to decompose it via intuition, so separation of concerns, and not use a specific normal form. That's another thing I could do. You should understand losslessness, that's easy to check, join the tables, and you should understand the basics about dependency preservation. So that's basically all the content that we've covered in this class. If there's anything you think is missing and you want to ask if it's on there, let me know. I can tell you if it's important or not. But now in the last 3 minutes, so are there any questions? Let's start with that. Are there any questions about the content or the format? Yeah.
For relation algebra, will be allowed the access to relax?
To the what?
To relax?
Yes, you'll have access. You can use Relax for that. I'm not going to ask you to write a relational algebra expression, though. I have other ways to test that. So relational algebra is, well, I don't need to go into my whole philosophy about that. But some of you may have found it very useful, and others are like, I never want to see this again. And that's totally, totally valid, whichever way you feel about it. But as you can see in the functional dependency theory, it came up again. Yeah, so relational algebra will be on the exam. It's not going to be very theoretical. It's not going to be writing an expression. I may ask you to convert between SQL and RA or RA to SQL, like as a matching problem or something like that, instead of writing the expression. Now, any other questions about the exam? We end at 1:50, just double check. Okay, if there are no questions about the exam, I know it's a 5-week course. Again, I know it's dense material. Please try not to panic about this exam. If this exam goes horribly wrong, and I've been doing this long enough to know that the first time you teach a class, things don't always go as planned, or there's other issues that you don't foresee happening. If this exam goes horribly wrong, an adjustment will be made, whether it's during the exam or in the grading of the exam or the final grade. So don't worry too much about that. A lot of you are in the same boat, so don't worry about that. I consider myself a pretty empathetic person. Did somebody have, yeah.
What do you mean by adjustment?
Adjustment? What do I mean by an adjustment? I'll let that be a surprise. If there's a technical problem during the exam, I can't expect everybody to finish in 3. I've had this happen. I changed the due date on an exam once. I added extra 15 minutes. Half the class got kicked out of the exam and could not get back into it. I had to make an adjustment so that people did not get screwed, basically. So I'll let you use your imagination there. Or it could happen in the grading or in the final grade. Now, course aside, parting words. Many of you are looking for internships or jobs. I want to repeat what I said during lecture 1. The reason this is called a business analysis program is because when you create a new major at UCLA, you have to justify why we have this major and why another program can't satisfy it. This program could be satisfied by majoring in stats, perhaps, or some parts of CS or some parts of econ. But this is the School of Business, School of Management. So to justify, I'm guessing to justify, they named it Business Analytics. This does not mean that you need to be a business analyst, though. That is one title. You may be a data scientist. You may be a data analyst. You may be a data engineer or maybe even a DBA. I don't know. There's a lot of different career options you can take here. Focus on the job description, not the title. I learned this myself by focusing on data scientists. I've worked in various different places, was happy in some, unhappy in others, because the job description was vastly different. Many employers consider SQL to be something that can be learned on the job. So they don't teach, a lot of schools don't teach it to CS undergrads. You're getting it because it helps you. You're not CS, maybe you weren't CS undergrads, but it helps you here, give you an extra boost that you may need to help get you a job. Some companies don't interview in it at all. They expect you to learn it on the job. In others, though, they do interview you on it. I had a job once where I was expected to learn SQL on the job. It didn't work out well, so I didn't last in that job for very long. That's when I went back and learned SQL really, really well, enough to teach it and enough to become the team expert in SQL. So I learned from my failure here. And for you that are newer to this, no, none of you are going to fail. But if you struggled, learn from it, and you will learn from it, and you will get better from it. There's still a lot of time to improve on the SQL before you go for interviews and a job. Some of you will exclusively spend your time writing SQL, and others may only occasionally use it. I write SQL maybe once every 3 to 4 months. Believe it or not. That one job, the one I didn't last in very long, that's all I did. So it's a very, very wide spectrum here. I'm going to assume that all of you are going to use it every day. That's why we have this class. Just kind of drill it into your head. I believe you will have an advantage here. All right. I'm happy to keep in touch with people in terms of if you have questions about the class or about this career in general or anything else. I hear from my computer science students frequently in the past. So if I can be of any other further assistance to you, please don't hesitate to contact me. Through at least December, I'm keeping this Anderson email. After that, though, it's safer to contact me on my CS email, which is rrosario@cs.ucla.edu. I want to thank you all for a great 5 weeks. In particular, I want to thank our TA, Lalit, who has helped out a lot of you and spent a lot of hours helping you out. It takes a village to put together a class like this, especially the first time. We don't have a grader, so I can't thank them. It's our TA and myself. But I also want to thank all of you for your hard work this quarter, but also for your patience as we go through learning this together, what it takes to put together a SQL class, and where we can speed up and where we can slow down. I know that can sometimes be frustrating and or confusing. So I want to thank you for a great quarter and for your patience and for your hard work this quarter. So thank you. Thanks. All right. Okay, we were 3 minutes over. Wow. Okay, great. We got through that. Congratulations. And best of luck on the final. We're here to help you.